Okay, so now I want to look at these three problems. So let S be a subset of Rn. What does it mean for S to be a subspace? Well, there's basically two or three things depending on how you count. One, S needs to be non-empty. This is an important one that seems kind of silly, but it's important. So S is non-empty, and two, if V1 and V2 are in S, and C1 and C2 are real numbers, then C1 V1 plus C2 V2 is in S. Okay, so in other words, we say that S is closed under linear combination. So let me write that up here. You won't have to write this for the test or anything like that. I mean, this isn't part of the solution. I just want to say this. So the phrase is S is closed under taking linear combinations. In editing, I see that what I'm writing is off the screen. You'll just have to wait until I upload this document later, but I'm only writing down what I'm saying. So just write down what I'm saying. All I'm doing is writing down S is closed under taking linear combinations. This phrase, a set being closed under doing certain operations, is one that comes up a lot in math. And if you go on in your math education, you'll see more of this. Okay, so number 12, show that the set x plus y plus z equals 0 is a subspace of R3. Okay, so first things first, we need to show it's non-empty. So 1, if you look at the vector 0, 0, 0, this is in S. Why is it in S? Because 0 plus 0 plus 0 equals 0. And what does a vector have to do to be in S? Well, you just add the entries together and it's equal to 0. Okay, 2, we need to show that linear combinations are in S. So let's say V1 and V2 are in S. Okay, then we'll say V1 is x1, y1, z1. So we're going to do C1 V1 plus C2 V2. Okay, this is in S. Why? Because of the following. Whoops. Because the sum of these two vectors is C1 x1 plus C2 x2, C1 y1 plus C2 y2, C1 z1 plus C2 z2 satisfies C1, so it's the top coordinate plus the middle coordinate plus the bottom coordinate equals 0. So C1 x1 plus C2 x2 plus C1 y1 plus C2 y2 plus C1 z1 plus C2 z2 equals, and now I'm just going to get all of the 1 index stuff together and all of the 2 index stuff together. So this is C1 times x1 plus y1 plus z1 plus c2 times x2 plus y2 plus z2. Now these two guys, x1 plus y1 plus z1 is equal to 0, and x2 plus y2 plus z2 is equal to 0. Why? Well, x1, y1, z1 is in S. And what does a vector have to do to be in S? The sum of its coordinates is equal to 0. So this is C1, 0 plus C2, 0, and that's equal to 0. Okay, so this vector, the sum of the two vectors, satisfies the property that the first entry plus the middle entry plus the bottom entry, the sum of those entries is equal to 0. Okay, so it's in S. All right, and so now question 11 is to find a basis for this subspace. Okay, so there's I'm going to do this basically 2 ways. Hopefully I have enough room. I'm going to do this 2 ways. Obviously on the test, you only have to do it 1 way. Okay, so if you look at the equation x plus y plus z is equal to 0, what this tells us is x, it tells us that x is equal to minus y minus z. Okay, so the only restrictions is that x is just equal to minus y minus z. So y and z can be whatever you want them to be as long as x is just equal to minus y minus z. Or you could write this as minus y plus z. So the vectors, so another way to write s would be the following. All vectors of the form minus s plus t st, where s and t are in R. Okay, but this is just equal to the set of vectors of the form. I'm going to just separate the s and t stuff. So this is minus 1, 1, 0 plus t times minus 1, 0, 1, where s and t run through the real numbers. But notice this is exactly, sorry, I have too many equal signs. But notice that this is exactly just the linear span of the vectors minus 1, 1, 0, and minus 1, 0, 1. Okay, so these two vectors are a spanning set for S. Are they linearly independent? And to show they are linearly independent, what do we need to do? Well, we could put them into a matrix and row reduce and show that there are no free variables. That would be one way to do it. But we could just say also they are linearly independent. These two vectors are linearly independent because neither is a multiple of the other. Okay, so they're linearly independent. What does it mean for them to be linearly independent? It means that none of the vectors is a linear combination of the other vectors. Since there's only two vectors, that just means that neither of the vectors are a multiple of the other vector. Okay, so it's a basis. Okay, now another kind of slick way to do this problem, you could basically just combine steps 12 or problems 12 and 13 together. Is the following: is to say something along the lines of the following. Note that S is the null space of the matrix 1, 1, 1. Since if this is the matrix, MV equals 1, 1, 1 times X, Y, Z, and this is equal to X plus Y plus Z, which is exactly the equation, the defining equation there. Okay, so the S is equal to the null space of a matrix. So that tells us it's a subspace. Okay, because the null space of a matrix or the null space of a linear transformation is a subspace. Okay, so how can you use this to actually solve problem number 13, which is to find a basis? Well, we're going to take this matrix and row reduce it. We want to take this matrix and get it into reduced row echelon form. Well, what does a matrix have to be in reduced row echelon form? Well, it needs to be in row echelon form, which means that for every pivot, the entries underneath it are equal to 0. Well, the first one, that's the only pivot, and there are no entries underneath it. Okay, that's fine. And all of the pivots need to be 1. Okay, that's fine. Perfect. And all of the pivots need to be strictly to the right of the pivot in the row above it. Well, there's only one row, so that's also kind of vacuously satisfied. And then what does it need to be in reduced row echelon form? Well, in addition to that, all of the pivots above, or all of the entries above each pivot need to be equal to 0. Well, again, the first one, that's the only pivot, and there's no rows above it. So this is trivially in reduced row echelon form. And this tells us that the second variable and the third variable are the free variables. And so the null space of this matrix is just going to be all vectors. Well, if we solve this, we'd get x1 equals, we'll say x is equal to minus y, y is equal to free, sorry, I messed that up. I messed that part up. X is equal to minus y minus z, y is free, and z is free. So we'll say y is s, and we'll say z is t. Okay, so in other words, the solution set xyz is equal to minus t plus s, st, or we could write this as s times minus 1, 1, 0, plus t times minus 1, 0, 1. And now it's something similar. You can continue and do something similar that we did over there. Okay, so this is basically two different ways to think about the problem. Obviously, they are very similar ways to think about this problem, but just sort of reflect on these ways that I'm telling you to think about the problem and kind of understand how they relate to each other. Because there obviously are going to be questions like this on the exam. And aside from that, this is kind of a concept that's important in this class.